Welcome viewers to the second segment of the first lecture for the online series of lectures for the course of Algebraic Topology. In the previous segment, we proved that homotopy and path homotopy are both equivalence relations. In this segment, we will start the discussion on products between two paths. Okay, so here is the definition of product between two paths. So if f is a path in X from x0 to x1, and if G is a path from x1 to x2. Okay, so this means that f of 0 is equal to x0 and f of 1 is equal to x1, and G of 0 is equal to x1 and G of 1 is equal to x2. Okay, we define, so if this is the case, we define the product f star G of f and G to be the path h in X given by h of s is equal to f of 2s for s belonging to this interval, and h of s is equal to g of 2s minus 1 when s belongs to this interval. Okay, so this is the definition of h. One immediately checks that h of 0 is equal to f of 0 and f of 0 is equal to x0, right? And h of 1 is, so this formula will hold now, is g of 1 and g of 1 is equal to x2, and one can prove that h right h the map h from I to x is a continuous well-defined map by using pasting lemma. Why? Because I can be the topological space I equipped with the subspace topology inherited from R can be written down as a union of two closed intervals 0 1 half and 1 half 1. Okay, and f is a continuous map from this interval to x, since f is a path, and g of 2s minus 1 is a map from this interval to x, since G is a path. Okay, and then by means of pasting lemma, one sees that H is a continuous map on the from I to X. Okay. Okay, this is how one shows that H is a well-defined continuous map. Okay, so one also sees that, looking at the expression of H, that H is the path whose first half is the path F, and whose second half is the path G, right? So the product operation, that we have just defined, F star G is the same as H. Okay, this product operation on paths induces a well-defined operation on path homotopy classes, okay, defined by the following. So if I choose the path homotopy class of F and take the product of that to the path homotopy class of G, then this is exactly equal to the path homotopy class of F star G. Okay, so let us quickly check this one. Okay, so this is denoted by equation number 2 in the notes. So let me erase everything. So we are going to verify this. Okay, so how do we check the well-definedness of these two products? So we choose F prime such that F prime is path homotopic to F. Okay, so that F prime also belongs to this class. Okay, similarly, we choose G prime belonging to this class, so that G prime is path homotopic to G. Okay, now if we can show that F star G is path homotopic to F prime star G prime, will be done proving that this is well defined. Okay, the star product that is induced on the equivalence classes is well defined. Okay, so this is all we need to check given these two path homotopy. Okay, so since F is path homotopic to F prime, there is a path homotopy. We choose that path homotopy F to be the continuous function from I cross I to X. Okay, defined in the usual way, and we choose the path homotopy between G and G prime to be the function big G from I cross I to X. Okay, okay, now we define our function H from I cross I to X in the following way. H s comma t is equal to f of 2s comma t for s belonging to 0 and 1/2, and this is equal to g 2s minus 1 comma t when S belongs to 1/2 and 1, this interval. So now the claim is that H from I cross I to X, we number this equation by 3. This defined by 3 is a path homotopy between F star G and F prime star G prime. Okay, so this is the claim. Okay, we construct a table as before. I need to erase everything. I need a lot of space. So I construct a table. We are given that F is path homotopic to F prime, and we are also given that G is path homotopic to G prime, and we choose F to be a path homotopy, here for the path homotopy between F and F prime. And from the definition of path homotopy, we have 4 equalities. F s comma 0 is equal to F of s, and F s comma 1 equal to F prime of s. Now we have F 0 comma t is equal to x 0. Okay, so remember that F is a path from x0 to x1, right? So is F prime. Okay. F prime 0 is x0, and F prime 1 is x1, right? And G is a path from x1 to x2, so G0 is x1, and G1 is x2. So is G prime 0 is x1, and G prime 1 is x2. Okay. Now G is path homotopic to G prime, so let G be a path homotopy between G and G prime. Okay, so that big G at s comma 0 is G of s, and big G at s comma 1 is equal to G prime of s. Also G 0 comma 2, sorry, G 0 comma t is x1, and G1 comma t is equal to x2. Okay. Now recall the definition of H. We defined H as H s comma t as f 2s comma t for s between 0 and 1/2, and we define hst to be equal to g of 2s minus 1 comma t when s lies between 1/2 and 1. This is how we define H. Now from the definition of the product, we immediately see that f star g at s is equal to f of 2s for S from S belonging to this interval, and this star, the product is equal to G of 2S minus 1 for S belonging to this interval. Okay. Okay. So now I write this to be equal to f of 2s comma 0 when s belongs to this interval, and g of 2s minus 1 is big G of 2s minus 1 comma 0 when s belongs to this interval. Okay. So it follows from this table. Look at here. This. Just substitute s with 2s. Then you will have small f of 2s to be equal to big F of 2s comma 0. Okay. And from this you will get G of 2s minus 1 comma 0 to be equal to small g of 2s minus 1. Okay, and look at this definition now. If you plug in 0 here for t, if you take t to be 0 in this formula, you will get exactly this expression on the right side, so that this is h s comma 0. Okay, this is numbered as equation number 4 in the lecture note. Okay, so we have shown that f star g at s is equal to h of s comma 0. Good. Now f prime star g prime at s, according to the definition of product between two paths, is f prime at 2s, and this formula holds when s belongs to this interval 0 1 half, and the formula for the product of these two paths is going to be equal to g prime of 2s minus 1 when s belongs to this interval 1 half and 1. Okay, and this is equal to, we'll get back to the table again, and we see that using this equality, we see that this is nothing but big F of 2s comma 1. This is the case when s belongs to this interval, and g prime of 2s minus 1 is going to be big G of 2s minus 1 comma 1, and this is the case when s belongs to this interval. Okay, and now by looking at 4 we see that, so we just take t to be 1, right? And we immediately see that this is nothing but h s comma 1. Okay. Good. Now let me erase these things and just write the result of what we have proved right now. So we have proved that f star g at s is equal to h of s comma 0, and we have shown that f prime star g prime at s is equal to h of s comma 1, okay, from the table and equation number 4. Now again, using the table and equation number 4, we see that h of 0 comma t, so h of 0 comma 2 t is equal to this formula holds for s equal to 0, right? So h of 0 comma t is going to be equal to f of 0 comma t, and f of 0 comma t is x0, right? Okay, so I think this is erased. I should rewrite it here. F of 1 comma t is x1. Okay, so h of 0 comma t is x0, and h of 1 comma t, so we plug in 1 in this expression of hst so so when we take s to be equal to 1, we get the second formula holds, and this is just g of 1 comma t, right? And g of 1 comma t is x2. Okay, so we have this, and we have this, and we have this. So together we see that hs comma 0 is equal to f star g at s, and h of s comma 1 is equal to f prime star g prime evaluated at s. Then h of 0 comma t is equal to x0, and h of 1 comma t is x2 for all s and t in I. Therefore, h from I cross I to x defined by this equation is indeed a path homotopy between f star g and f prime star g prime. Okay, now we have the first theorem of today's lecture. So now, okay, so a while ago we proved the that the product between two paths such that the final point of the first path is the initial point of the second path is a well-defined product um, in the context of equivalence classes as well, meaning that it extends to the classes, this product. This is what we have checked a while ago. Now we have the first theorem stating that the operation star has the following properties. One, associativity. If it tells us that if the class of F star, the class of G star, the class of H is defined, and it is defined if the final point of F is the same as the initial point of G, and the final point of G is the same as the initial point of H, then this product is defined. Okay, so if this guy is defined, so is this. Okay, so the associativity means if one is defined, the other is automatically defined, and they have to be equal, and they are equal. This is what associativity states. The second property is the existence of right and left identities. Right and left identities. So let me state it first. Given a point X in the topological space X, let E sub X denote the constant path. E sub X from I to the topological space X, carrying all of I to the point X in X. Okay, that's why you have sub X, and it means that all of I is being carried to this single point of big X. Okay, now if F from I to X is a path from x0 to x1 in X, then the product of the class of F star, the product of the class of E sub x1. Okay, so this is the path from I to, this path is, okay, E sub x1 is a function from I to this single point x1, right? This is the singleton x1, where x1 belongs to x. Okay. All right. So what does it mean in terms of path in x? It means that this function evaluated at 0 is going to be x1, and this function evaluated at 1 is also x1, since it's a constant path. So it's a path from x1 to itself. Okay, so f is a path from x0 to x1, and e sub x1 is a path from x1 to itself. So the product, using our definition of product between two paths, is going to give us a path from x0 to x1, and the existence of right identity tells us that this is going to be exactly the same as the path f, the class of path f in this case. Okay. Okay, and for the right identity, the class of e sub x0 star, the class of f, is the same as the class of f. This is the left identity, and this is the right identity. Okay? Okay, good. Now, the inverse, which is the third one. Inverse. Given the path f in x from x0 to x1, okay, which means that f of 0 is equal to x0 and f of 1 is x1. Let f bar be the path defined by, so we're defining the function f prime from x to I, f bar s equal to f of 1 minus s. Okay, sorry, so f bar is not from x to I. F bar is a map from I to x. Okay, in this way, this is the way we define f bar. Okay, so it is called the reverse of f. This f bar, it is called the reverse of f. And is a path. It's clearly seen to be a path in x from x1 to x0. Why? Because you immediately see that f bar at 0 equal to f of 1, which is x1, and f bar at 1 is going to f of 0, which is x0. So it's a path from x1 to x0, which is called the reverse of f. So if this is the case, then f, the class of f star, the class of f bar, is equal to e sub x0. We already defined e sub x0 is the is this left identity, and the class of f bar star the class of f is equal to the class of E sub x1. E sub x1 is a right identity. Okay, so this is theorem 1. Okay, so we'll prove this theorem in this lecture. Okay, so before that we take a break. We'll be back with the proof in the third segment. Thank you for attending the second segment of the first lecture.